Welcome to Debug Log, software engineering war stories, architecture decisions, and lessons learned the hard way. Let's dig in.
The system was operating fine, or so it seemed, until logs started showing connection issues. Then, memory usage climbed steadily, hitting gigabytes, ultimately crashing the server. The culprit? A million dormant goroutines.
A million, not a typo. This wasn't a case of some obscure memory allocator misbehaving. It was the Go runtime accumulating lightweight concurrency units, each holding on to resources until the system buckled. The kind of problem that makes you rethink lightweight.
And this wasn't in some niche experimental service. This was an authentication gateway for Kubernetes, a critical piece of infrastructure designed to sit right in front of the API server.
Exactly. The very definition of a component that absolutely cannot fail. And the postmortem details how the pursuit of custom, highly tuned authentication, coupled with an incomplete understanding of Go's concurrency primitives in a networked service context, led directly to this cascade. It's a textbook example of how complexity breeds fragility, especially in security-sensitive areas.
To unpack this million goroutine leak, when discussing goroutines, the common wisdom is that they're cheap, efficient, Go's answer to lightweight threading. How does one accumulate a million of them accidentally?
The article points to a few factors, but the primary mechanism was essentially orphaned network connections. The Auth gateway was proxying requests to the Kubernetes API server. When a client connection to the gateway was closed or timed out, the corresponding upstream connection to the API server wasn't always being cleanly shut down or released.
So a client drops, but the gateway holds on to the connection to the API server.
Not quite. It's more subtle. The gateway spawns a Go routine for each incoming client request to handle the proxying logic. This Go routine would establish an upstream connection, stream data, and then, ideally, clean itself up. The issue arose when the client-side context for a request was canceled or timed out, but that cancellation didn't correctly propagate to the upstream Go routine responsible for proxying.
Meaning the upstream goroutine kept waiting, consuming resources, completely unaware the client had already given up.
Precisely. It was stuck in a perpetual state of waiting for a response that would never come, or trying to write to a connection that was no longer active on the client side. Each of these stuck Go routines, while individually small, collectively added up. They weren't truly leaking memory in the sense of unreferenced heap objects. Rather, they were live, active Go routines that were simply never terminating, holding on to their stack space, any associated channel buffers, and network resources.
It's like having a million waiters in a restaurant, each assigned to a table, but the diners left hours ago, and the waiters just stand there, holding their order pads, waiting for a signal that will never arrive.
A fair analogy. And the Go garbage collector, for all its sophistication, doesn't collect live Go routines. If a Go routine is reachable and active, it stays. The problem wasn't memory allocation in the traditional sense. It was memory retention due to an unbounded increase in concurrently executing, albeit idle, logic paths.
This highlights a common pitfall with Go's concurrency model. While Go routines are cheap to start, they're not free. And if you don't manage their life cycle, especially in I/O-bound operations, you can quickly run into trouble.
Absolutely. The article emphasizes that context cancellation, while powerful, needs to be meticulously propagated through every layer of a concurrent operation. If a single I/O call or a channel read doesn't respect the context.done signal, you have a potential leak point. In this case, HTTP server.shutdown was also a factor, specifically how it handles active connections during graceful shutdown. If not all connections are properly closed or handled within the shutdown timeout, they can become orphaned, leading to these zombie Go routines.
So the gateway was designed to handle authentication for Kubernetes. What specific challenges does an auth gateway present in a Kubernetes environment that might have exacerbated this?
Kubernetes authentication is inherently complex. The API server has a pluggable authentication mechanism. An auth gateway typically sits as a reverse proxy or an admission controller, intercepting requests, validating credentials, perhaps an OIDC token or a custom API key, and then forwarding an authenticated request to the Kubernetes API server. This means it's a critical path component. High traffic, low latency requirements, and absolute correctness are paramount.
And the article implies that part of the lessons learned was to move towards boring authentication. What does boring mean in this context, and why is it preferred over something custom?
Boring in this context refers to using established, well-understood, and widely implemented authentication protocols and libraries. Think OIDC, OAuth 2, SAML. It means avoiding custom-rolled authentication schemes, unique token formats, or bespoke credential management. The engineers initially opted for a more custom solution, likely aiming for specific performance or integration characteristics.
Which is a common temptation, right? To build something that feels perfectly tailored to your needs rather than adapting to an off-the-shelf solution.
Precisely. The allure of optimizing or having full control often leads to reinventing wheels, many of which have security vulnerabilities or subtle operational failure modes that have already been discovered and patched in standard implementations. The article argues that for something as fundamental and security critical as authentication, innovation should be viewed with extreme skepticism.
So the boring approach would be to, say, use an existing OIDC provider with a well-vetted Go library for OIDC client functionality and avoid custom token issuance or validation logic.
Exactly. Leverage battle-tested libraries, adhere to standards, and minimize the custom surface area. The cost of a custom authentication system isn't just the initial development. It's the ongoing maintenance, the security audits, the patching of newly discovered vulnerabilities, and the sheer cognitive load of understanding its intricacies. When you have a Million-Goroutine memory leak in your custom auth gateway, the cost becomes very tangible.
It's a classic trade-off: perceived flexibility and optimization versus the robustness and security inherent in widely adopted, scrutinized standards. And in security, robustness often wins.
It should. The report highlights that their custom solution introduced a significant amount of complexity, including custom token issuance and validation, which had to be maintained and debugged. This increased the attack surface and the likelihood of subtle bugs like the goroutine leak. Had they leaned more heavily on standard OIDC flows handled by a mature library, many of these issues might have been mitigated or entirely avoided.
So going back to the technical fixes for the leak, how was it ultimately diagnosed and resolved?
Profiling was key. They used Go's pprof tool to inspect the number of active goroutines, which revealed the unbounded growth. Once they identified that the goroutines were blocked on I/O operations or channel reads, the investigation shifted to context propagation. The primary fix involved ensuring that context with timeout and context with cancel were used consistently and correctly across all network operations, both inbound and outbound.
So every single I/O call had to respect the context. If the client drops, the upstream call needs to know immediately.
Correct. And also handling server shutdowns more gracefully. They implemented more robust logic to ensure that during a HTTP server.shutdown call, all active connections were given a strict deadline to complete, and if they didn't, they were forcibly closed. This prevents lingering connections from holding goroutines indefinitely.
It sounds like a deep dive into the nuances of Go's net/HTTP package and context module.
It was. The lesson is that while Go provides powerful primitives, the responsibility for correct lifecycle management, especially in high concurrency network services, still rests with the developer. The default behaviors aren't always sufficient for complex, high-throughput scenarios. This incident serves as a stark reminder that even seemingly small omissions in context handling can lead to catastrophic resource exhaustion.
And the broader implication, beyond the specific Go issue, is about understanding the underlying mechanisms of your tools. It's not enough to know how to launch a Go routine, you need to understand when it terminates and what happens if it doesn't.
Exactly. It's about developing a mental model of resource lifecycle in a concurrent system. The Go runtime is very good at what it does, but it can't magically infer your intent for a Go routine that's blocked indefinitely. You have to explicitly tell it when a task is no longer relevant, via context cancellation or explicit timeouts.
So, looking back at this postmortem, what are the core insights that an engineer should take away from the Million-Goroutine incident and the push for boring authentication?
First, understand the lifecycle of your concurrency primitives.
Goroutines are cheap to start, but expensive if they never end. Explicit context propagation is non-negotiable for robust Go services. Second, for critical infrastructure, especially authentication, prioritize established, boring solutions over custom innovation. The cost of a custom solution's complexity and maintenance almost always outweighs its perceived benefits. Third, thorough profiling and instrumentation are vital. The problem was hidden until memory bloat became undeniable, but earlier profiling could have caught the Go routine accumulation.
And finally, a reminder that building something truly resilient means designing for failure at every layer, including managing the implicit resources like Go routine life cycles.
Indeed, it's a testament to the idea that simplicity often leads to greater reliability, especially when dealing with distributed systems and security components. Sometimes the most innovative solution is the one that simply works without drama.
So if you're building a new service, are you defaulting to the simplest, most standard solution first, or are you still tempted by the promise of custom optimization? And how deeply are you truly understanding the lifecycle management of your chosen concurrency model?
That's a wrap on this debug log. Join us next time for more engineering war stories and hard-won lessons. If any of this hit close to home, subscribe and tell your team.
Ship it carefully.